Hi, I'm Francesco Cosentini, and this is my lab report for Physics 2211 about straight line motion at constant velocity. The purpose of this lab report is to analyze the video of an object moving at the same speed without changing direction, then to analyze the video using Tracker to extract the object's position and the corresponding time. Then it is necessary to construct a computational model that accurately describes how the motion of the object is related to Newton's second law of kinematics. In this lab report, I will analyze the movement of a person that was walking on a straight line, constant speed, from a pillar to a brick structure in my Larsen saw. But before evaluating everything with Tracker, let us first review a little bit about physics' second law, Newton's second law of kinematics, which is this following equation. And then if you expand delta V into final velocity minus initial velocity, you'll get the following equation. And the final velocity, determined with Newton's second law, will be applied for the law of kinematics that describes the displacement of a straight line motion at constant velocity, which is the following equation. In order to evaluate the velocity from the movement recorded from the video, the application Tracker will be used. And the object taken into consideration will have as center of mass put into consideration. The center of mass of a person is in the area of the abdomen of the person, according to the physics module of the center of mass from University of Tennessee in Knoxville. After the following data was taken into consideration, the clip settings taken into consideration were the following, which will be used to see the time. Then, I set up a coordinate system with the person moving towards the positive direction of the x-axis, and then the video, the width of the door, was used to calibrate the dimensions in the video. Since the person is moving at constant velocity, I can select any two x positions and the corresponding time positions available. But to make things easier, I will get the first two x positions and the first two time data to determine the velocity. And I'll ask the final time to be taken into account to be used as the determining condition for the computational model. Since the time interval used will be really small, the time step will be 1,000th of a second in order to get the most accurate position. Then, since the time step will always be the same, in order to determine the final position of the object, initial position will be used to determine the final position, which is this piece of code. And in order to determine the ball velocity, this following piece of code will be used, with all the previous conditions given in this piece of code above. But in order to determine the final velocity and the final position for every time step, it will be necessary to resort to a while loop. And the terminating condition will be when t is equal to the final time evaluated with Tracker. And when the code is run, we will also get the data obtained with the CSV file. The results obtained can be seen from this Excel spreadsheet obtained. From the computational model, it was possible to determine that the velocity was equal to 2.030 meters per second, and from the experimental data, the velocity was equal to 2.316 meters per second. The rate of error resulted to be 12%. Then the final position from the computational model resulted to be 2.030 meters, and from the experimental data was 2.295 meters. The rate of error resulted to be 13%. Although the slopes are different, it was possible to see that the computational model was close to the experimental data, but not extremely accurate. For the model to be closer to the experimental data, if to be more accurate, the error for both the final position and the velocity would have to be less than 10%. However, from the experimental data, it was possible to see that the data points with respect to time were in line, since the r squared was really close to 1, making it possible to presume that the position and time are directly proportional. Both the computational model and the experimental data describe displacement and time as directly proportional. Some possible reasons why the computational model failed to be accurate enough was because the velocity used for the computational model was too low compared to the average velocity found from the experimental data. However, if the velocity found used for the computational model was closer to the velocity determined in the computational model, then the data points of the positions with respect to time would be in line, and then the slopes be even closer. Also, the person was not moving on a perfect straight line. Also, the person started to slow down when it was heading towards a brick column. Because the position and time are directly proportional in both scenarios, then the net force on the person has to be equal to 0 at every single time interval considered. From the combination model, the position and time were directly proportional because net force was set to 0, and also Newton's second law were also taken into consideration. Since time and position were directly proportional in experimental data, then it was possible to see that net forces acting on a person recorded was equal to 0, since time was known to be non-zero and the mass was 54.4 kilograms. Therefore, Newton's second law was applied in a straight line motion at constant velocity because since no force were acting on the person, because they were all cancelled, the person from the video was still moving on a straight line at constant velocity because there was not any force that induced the person to move faster or to move slower. In conclusion, it was possible to understand that when an object moves on a straight line at constant velocity, the net forces acting on the object will always be null because net force always induces change in velocity on a person. This is my live report. Thank you for watching.